Go.
Hi, my name is Krishna Patel, and I'm excited to share my findings today about the last 3.5 years of research I've done in the lab of Dr. Nicholas Bentley, an assistant professor of biology right here in Penn's biology department. Now, at a high level, our lab employs various neurobiology and behavioral experiments to study survival drives like hunger, pain, and thirst. To maximize the probability of survival across different environments, we are hardwired with various types of internal signals so we can have a lot of various critical adaptive behaviors for survival and fulfilling these essential needs. For example, we seek nourishment in the form of food or water when an animal is hungry or thirsty, and we feel pain when we have an injury that signals the presence of a threat. Many of these survival drives, most notably those of pain and hunger, we've done a really good job conducting research that outlines them individually, but until recently there was very few studies done that really showed them when they were combined. This is what the research I and Dr. Bentley have been getting at over the last 3.5 years. Now, one thing we want to do is to introduce a competing need state, which means what happens when we introduce two of these survival drives at once. In this video, I'll be focusing on what happens when we stimulate hunger and pain at once, and how they are prioritized in terms of the neural mechanisms and signaling when they're triggered simultaneously. Now, in terms of past studies, there is a little bit of evidence that hinted that when you're hungry, you feel less pain, but there wasn't a great distinction or too many details on this, and there was no distinction between different types of pain. The types of pain we'll be looking at here are acute pain, which is it's best to think about this in terms of the type of pain you feel when you accidentally recoil after touching a hot stove. And then in opposition to acute pain, you have inflammatory pain, which is the more throbbing, chronic type of pain you feel after the injury is sustained. Now, to uncover more evidence about the circuits underlying these feelings of hunger and pain, we use starvation-sensitive agouti-related peptide, or AGRP neurons for short, as an entry point for investigation. Now, with that being said, I'll show you a little bit of the data that we collected to give a flavor of what type of research has been done. So the first set of graphs that we looked at in our research are these graphs here. And I know there's a lot of abbreviations. So again, AGRP stands for agouti-related peptide. NPY stands for neuropeptide Y, which is a type of signaling that occurs to the part of the brain, in this case called the PBN. That stands for parabrachial nucleus for short. And this is important because the PBN is where we saw all of these effects happen. We tested a lot of different sites, and out of the 10 different brain sites tested, the PBN was actually the last one we looked at, and this is where we saw all of these really cool effects that we believe can be huge entry points for future research. So what we see in the graphs here is generally, you see the dotted line in the background, and it might be a little bit faint, but generally that's the pain response a mouse has in the control setting when you don't give it any intervention at all. And the way we measure pain with these is you inject a noxious agent called formalin into the mouse's paw, and what you do to measure the pain is you see how much time they spend licking their paws as a proxy. Hence, you see with the dot in this first experiment for figure 5a, we started the intervention, which is PBN stimulation with the laser, right at 25 minutes. And right here, what you can see that is really cool is even though when they're in the control group, the mouse continues to be in a lot of pain up until the end of the experiment, giving stimulation of these AGRP neurons to the parabrachial nucleus, or PBN, you see the pain quickly decline and go quickly to zero, showing that there is a pain attenuation here. And it is important to note that these are all hungry mice, so this trend here is only seen in mice that are hungry, namely this trend where you see the attenuation of pain based on this PBN signaling. Then we also did a reverse experiment where we started stimulation early, and immediately you see this huge decrease in pain to almost nothing up until 25 minutes when we turned off the stimulation. And right here you see the data begin to converge towards that of the control group, or this dotted line. You also see this is the case, and this graph here just represents how much time the mouse is in pain, or how much pain the mouse feels. When you get no stimulation, a la the control arm, the mice are in the most pain, but once you induce stimulation of these hungry mice, with the AGRP to PBN neurons, you see the pain response goes down a lot. And this is the first major finding that we believe is is promising for future research. Next, you see we have our second set of graphs here, and this examines what happens when we block this PBN region and we block these neuropeptide Y signaling in hungry mice. So again, there's a lot of lines going on here, but what I want to call your attention to is you see this middle line here, which is the vehicle, which is just the control group essentially. And what happens when you stimulate the neuropeptide 1 antagonist, a la blocking the signal? What you see here is you see a convergence down to the control group where again pain is completely nullified. Now you see this again when you look at figure 6b, where when you give just the stimulation and you have nothing impeding the signaling, you get total no pain, because you have stimulation that, like you see here, attenuates the pain, and as a result, the mice doesn't lick much, as you see here. However, when you use this NPY1R antagonist, that effectively nullifies the AGRP stimulation, and as a result, the hungry mice see a lot more pain, as you can see by this huge spike in the big gap between these orange and gray lines, and also compounded by this much higher red bar, which is much more statistically significant than the vehicle. So, with that being said, let me recap by saying that this study results point to the discovery of a neural circuit implicating both hunger and pain, two essential survival drives that manifest in a variety of environments. Through central mediation by these AGRP neurons, we see that that NPY plays a critical role in mediating this dynamic interaction between hunger and pain. And we see that also in the graphs that although that the acute pain is what goes down immediately, i.e. what the pain you feel if you touch a hot stove, that you do still keep some of these remnants of inflammatory pain, i.e. the pain that, you see that although the acute pain isn't fully reduced, as evidenced by this gap between the x-axis and this bar, you see that the acute pain is preserved and the inflammatory pain is adjusted. And what's cool about this is because it really tells us a lot about animal behavior. So we know that if acute phase pain is unaffected by hunger and inflammatory phase pain is suppressed, we know that there is a hierarchy of sorts in play here, where if the acute pain is kept intact, this animal still has the initial stimulus to get away from any potential damage that might be done. You will still be incentivized to take your hand away from the hot stove, but you don't see the inflammatory phase pain, or you won't have that throbbing 25 or 30 minutes after the injury that can otherwise take away from you trying to find food that can help satiate your hunger. And one thing that's really cool is that this begins to help us discover other further neural circuits, and that is what we've been working on since these findings were procured. And what's also really exciting is that these results can be the future for other translational research geared towards pain management. And more specifically, this NPY1 receptor, which I talk about here, that could be a receptor for various for pain management, non-opioid related targets. And one of the most cool things that's most exciting is that there was a group of 300 neurons in this parabrachial nucleus region that when we stimulate them, we actually found the amount of pain was reduced as much as morphine. So as a result, we feel that this is a super promising target for both not only basic science research and translational research, but potential pharmacologic development in the time when the opioid crisis is really giving us a lot of problems and there's a really pressing need for new therapies. So with that being said, thank you for hearing my research on the intersection of hunger and pain, and I look forward to finishing this research up this semester. Thank you.